Hola a todas, bienvenidos y bienvenidas al evento Cómo empezó todo con Va començar tot. Este evento está enmarcado dentro de las actividades del Día de la Mujer y la Niña en la Ciencia y vamos a tener a 4 invitadas que son investigadoras del Instituto de Ciencias del Espacio. Perdón, creo que se ha acoplado el sonido por un segundo. Perdonad. Como decía, vamos a tener a 4 invitadas que son investigadoras del Instituto de Ciencias del Espacio y que van a participar con charlas de 5 o 10 minutos sobre su trabajo, su motivación para convertirse en científica, su carrera, etc. Y van a participar ya sea en catalán, en castellano o en inglés. Y por lo tanto el evento se va a desarrollar en los 3 idiomas y traduciremos si hay dudas, si es necesario o lo que sea.
Bon dia, hola a totes. També per a les persones que estan al YouTube us recordem que tenim un xat obert per si algú ens vol deixar preguntes o comentaris, també pot fer servir aquest canal. Y comenzaremos amb la Vanessa Graber. Vanessa, empezamos contigo. Vanessa viene de Alemania y va a hacer su charla en inglés, creo. Es astrofísica teórica, investigadora postdoctoral y estudia estrellas de neutrones. Trabaja en el proyecto RC Magnesia, que busca crear un censo de magnetars. Así que adelante, Vanessa, go ahead.
Okay, I will share my screen. Okay, I believe you can see my screen now. All right, welcome everyone. I will tell you a little bit about my story into science in general and academia. So as Clara just mentioned, I'm originally from Germany. I grew up in the south with a view of the Alps. And after an undergrad and a master's degree in Germany, I moved to the UK. And that was followed by a quick stay in Canada before I moved to Barcelona, where I'm right now. So I've been to quite a few places. Which is one of the things I will mention later, is sort of like the great attraction for me for being a scientist. But when I was sort of like in high school and had to decide what I wanted to do later on, I didn't really have like a proper idea what a scientist really is. I didn't have a scientist in my direct family. So there was no one really to talk to, but I had quite a few science teachers and teachers in general that sort of like made me curious about like, what is science, like this idea that you kind of like want to understand what is happening around you. So I didn't really know what like science really is or like how doing science really works, but I knew that I liked solving puzzles a lot. I like to ask lots of questions, so I was quite a curious person. And I was sort of always like trying to understand like how different things are connected and how things work. So those were sort of like the kind of like ideas I had in my mind. And I thought at that point that science is like a field where I can like sort of like follow these things along and actually like follow that kind of like approach to thinking and working in a way where I could like succeed sort of. So that's sort of like what drove me into science in general. And after my undergraduate experience in Tübingen, which is also in the south of Germany, I did a master's in astronomy and astrophysics. And one of the sort of like topics that came up in this were what is called a neutron star. So neutron stars are sort of one of the endpoints of what we call stellar evolution. So at some point, massive stars ran out of fuel and they sort of collapse under their own gravitational attraction. And one of these endpoints of stars that weigh something like 8 to 20 times the mass of the sun turn into a very compact object that has the size approximately of Barcelona, but weighs as much as the sun. So they're the densest forms of matter that we have in the universe. And because they are so extreme in all their properties, like magnetic fields, densities, rotations, all these kind of like properties that we have to sort of like describe physical objects also on Earth, they sort of like unite a lot of different types of physical theories. So when I was an undergrad and you have like all these different little subjects, what typically happens is you you learn one field by itself, and you sort of like learn a lot of the foundations of like what is going on. but it's very rarely that like you unite lots of different fields in some sense when you learn about the different like elements like thermodynamics, electrodynamics, classical mechanics. And when I learned about neutron stars for the first time, it was like sort of an eye-opening moment that I knew this is what I wanted to work on, because it kind of like unites all the different fields of like physics that I found exciting in one like individual topic. So I knew very, very little about astronomy and astrophysics before I started like this master's course. So I wasn't one of the people that in high school were part of like an astronomy like group or anything like that. I literally knew what the planets were, and that was about it. So I learned a lot more about these topics when I was actually an undergrad and a master's student. And yeah, I was totally like blown away by this kind of topic that I like to work on now. So I didn't really have like the classic approach into like astronomy and astrophysics that a lot of people have that work in this field, because I still can name about like 4 or 5 constellations. I know very little about the night sky, but for me, it's like the field where I can like do theoretical physics, and I absolutely love that about the field. So I mainly like use mathematical models and numerical methods to sort of like better understand the interior of these specific types of stars, and also look at like what kind of like techniques I can use to like sort of model more about these stars in their entirety. Because, for example, in our galaxy, we expect about 1 billion of these objects to be present, but we only know like a couple of thousand. So there's lots of like topics from different angles where you can try and understand this a little bit better. One of the other things that I wanted to mention is like why I now really like being a scientist, because I said originally that I didn't really have that much of an idea of what being a scientist really means. And I said that I really like the topic itself, but I think what makes it special for me is that being a scientist is a lot more than just doing the science or the maths. So I get to work with people from all over the world. I have friends on all continents now. I get to see lots of different places, and I like to travel a lot and experience like different cultures. And it's really been like sort of like an eye-opening experience of like moving to different places and learning more about the people there, but also about myself in that course. I like to really think about, like, as I mentioned earlier, like problems that are difficult to solve. So I can sort of like in my daily work, think about questions that we can't even answer yet and try and help find solutions or like paths to solutions. And by doing that, I sort of learn something new every single day. And that's for me really exciting. I also get to teach and talk about science a lot, which is something that I really like. And that is one of the reasons why I actually decided to pursue a career in academia, because I really like that like moment where you like explain something to someone else and you can see their eyes like get bright with like excitement about what you're working on. And that's something that I really like, on top of like using actually like the mathematics and the computational techniques to like understand more about our universe. And just to conclude, I also wanted to mention that scientists are also people. So we don't just do science. Lots of us have lots of different like hobbies that we like to do. One of the things, or some of the things that I really like to do is reading. I listen a lot to audiobooks. I'm particularly interested in crime. That's like my thing. I play lots of games, and I really like solving crossword puzzles, which is also something that sort of comes from my scientific driver. But I also like being outside a lot. I enjoy hiking, and I do a lot of yoga. And probably my biggest hobby, which is what I spend most of my time on when I'm not working and sleeping, is probably cooking and baking, because that's sort of like for me the perfect like creativity counterbalance that I have outside my work. Yeah, I think that's it from my side.
Great, thank you, Vanessa. So now I think we are going with Clara Dehman. Clara, you're next if you like.
Okay, hi. Let me share the screen.
Wait a second, I'll introduce you in Spanish and then
yeah, it's fine.
Okay. So Clara, ella viene del Líbano, ella está haciendo su tesis doctoral aquí en el ICE y la realiza sobre la evolución del campo magnético en las estrellas de neutrones. También participa en la Alianza Magnet, que es un proyecto de divulgación que tiene el instituto con una escuela en Igualada, la Escuela Gabriel Castellán. Y nada, Clara, when you're ready, the floor is yours.
I will. Okay. So hi, my name is Clara Dehman, and I am a PhD student at the Institute of Space Science. Well, I'm happy to have this opportunity today and to be telling you a bit about my scientific life and how I ended up being here. Yes, I come from Lebanon. It's this very little country that's located in the Middle East, and it have this 10 kilometer square, like an area of 10 kilometers squared, and I lived basically most of my life there. I grew up there. I come from the north of Lebanon, and I lived most of my life in Tripoli, and I did my bachelor degree in physics there. Then I wanted to continue my study and my master because I was really fascinated about higher education and about research. So I applied to scholarship. It's a European scholarship to study theoretical nuclear physics in Europe. The scholarship was about studying this master between 3 European countries, which are France, Italy, and Spain, and I got it. So as soon as I graduated, I moved to Europe. And the first place I went to during my master, or my first year of master, was Padova, which is a little city in the north of Italy. There I was mostly focused on nuclear and particle physics, but I also had some experience in experimental nuclear physics, where I have participated in an experiment to measure the fusion cross-section between the silicon-28 and the molybdenum 100 at the accelerator. It's a nuclear accelerator in the laboratory of Legnaros in Padova. And this work was done under the supervision of Professor Montagnoli and Stefanini, and we published this result basically last year. Then after my stay in Padova, I had to move for the third semester of my master to Caen, which is a city in the north of France, in the Normandy region, and there I did my third semester. The work was more focused on the theoretical nuclear physics, and I also had, as a part of the course, an internship on neutron stars. So that was my first work on neutron stars, and I was studying basically the equation of state of the neutron star, different equation of state of the neutron star using the so-called meta-modeling technique. This work was done under the supervision of Professor Gulminelli at the Laboratoire de Physique Corpusculaire de Caen Normandie, and this internship was sort of training for the master thesis. So after that, I had to come to Barcelona to do my master thesis, which was in theoretical nuclear physics, and the aim of the thesis was to basically extend an equation of state for neutron star. It's the BCPM equation of state to finite temperature. This work was at the University of Barcelona under the supervision of Professor Artur Pous, Xavier Viñas, and Mario Centelles. And here I am showing some few results of this work. So in the upper panel on the left, there is this equation of state at different temperature. Then on the right, I'm showing the mass radius relation with some observational limit that could basically tell if our work is valid or not. And in the last plot, in the bottom plot panel, I'm showing the tidal deformability as a function of the mass of a neutron star. And I am plotting at different temperature, and I am plotting this observational limit, and there is the arrow that is determined during the merging event between two neutron stars. And this like limit, it could tell us what could be the temperature or the limiting temperature of a neutron star during a merger event or during a hot environment like the merger event, and something between 0 and 21 mega electron volt. Then as soon as I graduated, I started my PhD, and I stayed in Barcelona. So basically, I moved simply from University of Barcelona to Autónoma de Barcelona. But this time I switched more to theoretical astrophysics rather than nuclear physics. And as mentioned, I am doing magnetothermal evolution in neutron star under the supervision of Dr. Nandareya and Daniele Vigano. In my PhD, there is kind of two parts. There is I'm working on the 2D magnetothermal code that's developed by our group in the last decades, 2 decades or 1 decade. But I'm also building the 3D-dimension magnetic evolution code. So I will mention briefly what is my main contribution in the 2D code, or the main project I did in the 2D code. The first was on the rate of crustal failures in young magnetars. So basically these crustal failures, it means that you have a lot of magnetic stress in the crust of a neutron star that are formed due to the dynamic and the evolution of the magnetic field. And then you have a solid crust, and then at some point this crust cannot handle anymore this stress. It's like you are pushing too much, and then it cannot fail and emit energy. And we are interested in looking at this rate of crustal failure because it can give us an idea about some events that are observed. They are called outbursts from magnetar. So it kind of help in predicting what's the rate of observed outburst. And the main result of this finding is that the key parameter was that one should look at the magnetic energy that's stored in the crust while doing such a kind of study, and not at the value of the dipolar component that could be really misleading. Then there is another project which is about a comparison between the thermally emitting luminosity that's observed from thermally emitting a neutron star, so the observational part, and the cooling curve that are predicted using the 2D code. So basically these are the internal cooling curve, and the dots, they correspond to different classes of neutron star. And we see that our magnetothermal code explains most of studied sources. To explain the very faint sources, we needed the very strong magnetic field, and to explain the very faint sources, they have very low luminosity. One need to have enhanced cooling by having this like a lot of neutrino emission, like a neutrino emission process that could produce or could emit a lot of energy and let the neutron star lose a lot of energy is basically the direct Urca process. And so to activate the direct Urca process, we needed to change to a different equation of state, which is the BSK24 equation of state at this solar mass, 1.6 solar mass, and that allowed us to activate direct Urca and decode with the superfluid gap that we are considering, and to basically explain the very faint sources. Then the main project of my PhD is more about having building this 3D magnetic code. So to do that, I have used something called the cubed sphere formalism. It's a peculiar formalism. Why did I use it, and what is it? So basically this cubed sphere, so basically in spherical geometry you have a problem at the axis. You have that the axis is ill-defined, problem of axis singularity problem. It's like, it means that some component of the magnetic field are ill-defined at the axis, like the b theta and b phi component of the magnetic field. And also you have that some geometrical element goes to 0, which means that whenever you are doing evolution, basically you cannot follow the evolution, because if you are dividing by 0 you get some nuns. And to solve this problem, one rely on this cubed sphere formalism, which tell you that this sphere gonna be separated into 6 identical patches. Each of these patches has its own coordinate system, and the difficulty of using such formalism is that the metric is non-orthogonal, so it's like non-orthogonal coordinate system, and one also need to do the connection between the patches, which was really a difficult task. But the good thing about using such a formalism is basically that it solves the axis singularity problem, and the radial coordinate of this coordinate is the same as the spherical one. I am showing briefly some tests, so basically of the work. So basically this is called the Bessel test. It's maybe the only test that have analytical solution to compare with. So we are testing here the diffusion of the magnetic field. So the magnetic field dissipates in time. What we do is that we have some numerical code that's running, and we have analytical solution that's also evolving in time, and we compare the solution. And if the two solutions overlap, that would tell us that basically the code is doing well, and that was the case here. And the lasting result is basically about the testing the two term of the induction equation The one is this is the ohmic term, the dissipative term, and this is called the whole drift term. I'm not showing any result, just to monitoring plot where basically they are for a 3D non-axisymmetric large scale crustal confined topology. So crustal confined means that you are confining your field in the crust only of the neutron star. In this first plot here on the left, you have the energy as a function of time. And one can see that this energy, the total energy is conserved in time, which means that our code is doing well. And on the right, you have the divergence of the magnetic field. And it's order of magnitude lower than two other parameters that have the same dimension. And that could also tell that the code is doing well. And that's it basically from my side.
Bueno, muchísimas gracias, Clara, por tu presentación. Ahora tendríamos en principio hasta el Catalan, pero veo que todavía no ha podido llegar. Así que si te parece, Alba, pasamos a la siguiente ponente.
Vale, ahora iríamos con Alice Borghese, si te parece bien. Alice es italiana y viene de una ciudad de Sicilia, es investigadora postdoctoral en el instituto y también es parte del proyecto Magnesia, igual que Vanessa, igual que Clara Dehman, y bueno, también su investigación también se centra en estrellas de neutrones y al igual que Clara Dehman participa en la alianza Magnet con la escuela en Igualada. Así que cuando quieras, go ahead in Spanish, in English.
English, still English. Thank you, Alba. So I'll share my screen if I manage. Okay. I know. No, right, stop. Sorry, I'm still not.
No worries, we have time.
Let me try again. Okay. Do you see the presentation? Okay, thank you. So good morning, everyone. So the event is called How It All Started. So I'm going to share with you how it all started for me. So as Alba said, I'm from Italy, and I was born in Messina, that a city in Sicily, the island that is in the south of Italy, as you can see. And I spent here all my childhood till high school in this little town called Nizza di Sicilia. Here I show you a picture of the view that I have from my balcony, so I could see all the sea and the sky. And this is one of the main reasons I decided to become an astrophysicist, because since a child I could see like all the stars at night and all this the black sky. So I was always wondering what is out there. So this is really like, I was always curious about the sky and the universe. After, during high school, I met a really nice math and physics professor that made me really passionate about physics. So physics became one of my also like the other passion of mine. And just really because I wanted to understand how things works and why things works. So at university, I decided to study physics, and they moved to the north of Italy in Padova, where I spent there 5 years studying physics, both for the bachelor and the master. And whenever I had the opportunity to choose like a course, I was choosing a course in astronomy. So just like to join my true passion in physics and astronomy. And already at that point, I knew that I wanted to become an astrophysicist because I really like these two things. So during my PhD, I managed to, let's say, achieve this dream, and I attended a PhD program in astrophysics at the Anton Pannekoek Institute in Amsterdam. So I moved more northern, and here I studied neutron star. So this was my first time I, let's say, meet neutron star in my scientific life. And after this, since May 2019, I'm a teacher at the Institute of Space Science here in Barcelona, and I did like a short postdoc in the group of where also Vanessa and Clara works, and then I won a fellowship, Juan de la Cierva fellowship from the Spanish government, and I'm still working and closely collaborating with the Magnesia group. So my research focused on neutron star, and as Vanessa explained, neutron star weight as much as the sun or a bit more, and are like the size of a large city. So this makes them the densest object we know in the universe. And I like to say like that we have a lot of different kind of people. We have a lot of different kind of neutron star. We have neutron star that like to stay, let's say, alone, and these are called isolated neutron star, or stars that like to have like a friend, a companion, and these are called binary system, where we have a neutron star that is rotating around a normal star. But also neutron stars are really fascinating object because they are the strongest magnet we know in the universe. And there are a particular kind of neutron star called magnetar that really like they have the strongest magnetic field we know, and this we cannot reproduce this strength on Earth. So this make really like unique laboratory to explore, investigate the condition to generate such a strong magnetic field. So what I study is neutron star, mainly isolated neutron star, but from an observational point of view. So neutron star emit, some of them emit in the X-ray, and we know that X-rays are absorbed by the atmosphere of the Earth. So we need satellites orbiting around the Earth and in the solar system. And thanks to that, I can collect my data. And here I'll show you an image from this from a satellite. So, and I mainly work with this image like every day. And from this, I can extract, infer my data and study the observational properties of neutron star. And I'm mainly interested in the effect that a strong magnetic field can leave on a neutron star emission. And also, as I said, because we have different kind of isolated neutron star, I would like to find a link between all these family. So find like observational evidence to build a unified picture to unify we call it the neutron star zoo, because it's like that we are wandering in a zoo and we see a lot of species. This is like what is happening in nature in the sky. So as Vanessa also said, we are like normal people. So we have hobbies. We just don't work, even if like we really like our job. So I like to spend my free time making bracelet, necklace with macrame. But I also really enjoy spending time outside and mainly hiking. And here you can see a few pictures. One is on Etna, the volcano in Sicily, and in Spain. I like sports in general, like climbing, yoga, running, but also what I really like to do during the weekend just to like relax, it's reading and writing poems. So I just like find 1 hour, 2 hours during the weekend where I sit in the sun and just read and write. So thank you for your attention. I think,
Bueno, muchas gracias a ti, Alice, por tu presentación. Y nuestra última ponente es la Simranpreet Kaur, però per presentar-la canviaré a l'anglès perquè ella acaba d'arribar de la Índia. So welcome, Simranpreet. Thank you for being here with us at this event. And as I was saying, Simranpreet Kaur comes from India and arrived very recently to our institute. She's a new PhD student investigating radio emission from exoplanets. And she is also the co-editor of a very cool YouTube channel about the wonders of the universe. And we're going to share the link through the chat in case you want to check it out. She's going to talk about the significance of science communication and outreach in motivating someone to pursue a scientific career. So go ahead, Simran.
Hi, thank you, Paula. Let me just share my screen. Okay, I'll just proceed like this only. There's some issue. Okay. So yeah, thank you, Paula, for the introduction. So yeah, hello everyone. As Paula already mentioned, my name is Simranpreet Kaur, and today I'll basically talk about how I got into science and how science communication played a significant role in driving me towards pursuing astrophysics in general. So yeah, talking about myself, I mainly come from India, specifically from north of India, from the city called Amritsar, a city which most of you must have heard about because of the magnificent Golden Temple, the magnificent Sikh temple, which is world famous. So yeah, I have recently joined ICE specifically on 17th of last month as a PhD student. And I'm also a science communicator, as Paula already mentioned. And I specifically contribute as an editor to the Global Astronomy channel, The Secrets of the Universe. And we are presently having like more than 1.1 million followers on Facebook and almost 300K subscribers on YouTube. At ICE, I will be mainly working with Dr. Daniel Vigano's group on the project Imagine, which is basically an abbreviation for imprints of magnetic fields in exoplanets. Here we will basically study about
Sorry for interrupting you, but here in the chat, people are saying that they cannot see the presentation. I don't know if you aim to see the presentation already. Or
yeah, actually, I couldn't share it due to some issues, so I'm just proceeding like this only without the presentation.
Okay.
Yeah.
Sounds good.
Okay.
Thank you. Sorry.
Yeah, no problem. So yeah, at IC, I'll be mainly working with Dr. Daniel Vigano's group on the project Imagine, which is basically an abbreviation for imprints of magnetic fields in exoplanets. Here we will basically study about the magnetic and thermal evolution of exoplanets along with the radio observations. And in this project, my work will mainly concern with the radio missions from exoplanets. And as you know, the radio missions are directly linked with the planet's magnetism. And the study can offer valuable insights into the planet's interior structure as well as their habitability. So this is what I'm like going to work in the long run. Right now, as I just started, I'm just mainly surveying literature and figuring out some exoplanet targets for a future proposals. So now coming to the theme of today's event, like how it all started and how I got motivated to take up science. Well, even in my high school, I always had an inclination towards science and teaching. And this is how, like, was just one day after completing my high school, I randomly decided, okay, I'll pursue graduation in physics. And so doing so in 2015, I joined a bachelor's degree in physics at Guru Nanak University in Amritsar. Over the years during my graduation, I was still not sure if I wanted to pursue research as a full-time career or not, or just I would like to go into like more some other works. So over the years, I took part in several summer schools and outreach programs. I did a number of projects like in IISER Mohali and IISER Kolkata, which are some renowned research institutes in India. And both these projects fell in the domain of basically the quantum computation. Doing so, I met Dr. Bindya Arora, with whom I gradually took a project on the black body friction forces. Here, we basically studied about how black body radiations can play a role in slowing down an atom. And while doing this project, I realized that, yes, this is something I really like doing. And this is when I actually decided that, okay, yes, research is a career for me. And this is when I decided, okay, after my master's, I'll go and do a PhD. But why specifically in astrophysics? Well, there's another motivation to this. Like in my graduation, I met a friend who was running this astronomy page, which Paula mentioned. And although we didn't have astrophysics as a subject in the university, but gradually we started exploring the subject on our own. Like we started going to libraries, started reading the stuff on internet, on like in books and everything. And over the years, I also started contributing to his page in the form of articles, scripts, and a number of other posts. And this is how I gradually developed my interest in astrophysics. And this is basically how I got inclined in this direction. And I must admit that working with this page and self-studying the subject out of passion, even if you don't have a subject in the university, and interacting with people over discussions who share the similar interests with you, sharing your doubts with them, and etc., all these things have played a dominant role in motivating me to choose astrophysics as my specialization in PhD. Having said that, I strongly believe that science communication can play a very crucial role in giving people insight about what is actually happening in science. And in some cases, they can also motivate them to pursue it themselves, just like it did in my case. Moreover, Science communication is a medium which helps to bridge gap between people belonging to scientific and non-scientific community. Like it offers them a platform to come together. Like people belong to different backgrounds can come together and can share ideas just like we're doing today. So yeah, here I would like to conclude, and with this I would end here. So yes, thank you Paul and Alba for organizing this session and giving an opportunity to be a part of this, even in the just when I just joined ICE. So I'm looking towards many such sessions in the future. So yeah, thank you for your time.
Thank you, Simranpreet. Thank you for sharing your experience. And now I'm going to switch to Spanish. Si tenéis alguna pregunta que hacer a las ponentes o cualquier consulta, podéis quitar el micro y preguntar.
Si os parece, estoy mirando por si hay preguntas en el chat de YouTube, pero veo que no. Entonces, si queréis, podemos dejarlo aquí, la emisión en directo, y continuar las preguntas de manera interna. Y podemos traducir entre si las preguntas son en un idioma y las respuestas en otro, si os parece bien.
Vale, pues lo dejamos aquí entonces y dejamos el evento online en nuestro canal de YouTube para quien lo quiera retomar, y para quien quiera saber más sobre el instituto, pues nos puede seguir en nuestras redes.